In this lesson, we're going to be looking at properties of parallelograms and exactly what it takes to make a quadrilateral into a parallelogram. So let's begin with the definition. A parallelogram is a quadrilateral whose opposite sides are parallel. So that means in the diagram here that these two sides are parallel and these two sides are parallel to each other. Now when we start talking about the parts of a parallelogram, we're looking at parts that are adjacent, consecutive, or opposite. And when we talk about opposite, we're looking at things that are straight across from each other. For instance, this pair of parallel sides are opposite one another. When we look at consecutive, it would be like taking angle in the top left, angle in the bottom left, or angle in the top left and angle in the top right, and setting them as being consecutive. So as we go through and begin defining or providing theorems for the properties of parallelograms, we're going to be talking about these terms quite a bit. So let's begin. We have quite a few theorems to get through in this lesson. Let's begin with theorem 6.3. This one states, if a quadrilateral is a parallelogram, then its opposite sides are congruent. So we've already defined a parallelogram as having its opposite sides being parallel. Now we add in this added condition that they must also be congruent to one another. Theorem 6.4 states that if a quadrilateral is a parallelogram, then its consecutive angles are supplementary. And this goes back to our same side interior angles theorem when we were looking at parallel lines and transversals, that if a set of parallel lines is cut by a transversal, the same side interior angles are supplementary. Well, since all we have are sets of parallel lines, whatever goes across are the transversals, and we have that same property present. Next, theorem 6.5 tells us that if a quadrilateral is a parallelogram, then its opposite angles are congruent. So we have opposite sides being congruent, opposite angles being congruent, and consecutive angles being supplementary. Now we can use these concepts and these theorems to help prove other properties inside of figures. Let's take a look at one such example. In this figure, we have a triangle with a shape built in, and our given information is that ABCD is a parallelogram. So this figure embedded here is a parallelogram, and that angle or side AK is congruent to side MK. So let's use this to prove that angle BCD, which is here, is congruent to angle CMD, which is here. So let's see what we can do with this. Well, we know that as we're going through here that ABCD is a parallelogram. So we'll start with that. So if ABCD was given to us as being a parallelogram, is a parallelogram, and you can use the symbol for parallelogram that's given, then angle BCD would be congruent to angle A, and that is by theorem 6.5. And we also know that AK is congruent to MK. That was a given. That means that angle A is going to be congruent to angle CMD, and that's by isosceles triangles theorem. Then using our transitive property, we could say that angle BCD is congruent to angle CMD, and that is the transitive property. Since both of them are congruent to angle A, they must be congruent to each other. So using our properties, our new theorems here, and a couple that we've pulled from previous lessons that have been studied, we were able to prove that angle BCD, angle A, and angle CMD were all congruent to each other. So these theorems will help us to build the relationships within quadrilaterals, and sometimes pulling back on ideas that we got from triangles and other shapes. So we do have a couple more theorems that will help us in continuing to define the properties of parallelogram. 6 tells us if a quadrilateral is a parallelogram, then the diagonals bisect each other. And theorem 6.7 states, so using theorem 6.6, and this diagram that is shown, what values of x and y would make it so that this is a parallelogram? Same concept we were doing before with our line segments. So because we know that in a quadrilateral diagonals bisect each other, we know from this diagram that 3y minus 7 is equal to 2x, and we also know that y is equal to x plus 1. Now, using systems of equations that should have been learned back in algebra, y is equal to x plus 1, that means where y is located in this first equation, that we can substitute x plus 1 into it. So what that will give us is 3 times x plus 1, the value of y, minus 7 equals 2x. Using our distributive property, we have 3x plus 3 minus 7 equals 2x. Subtracting 3x from each side using our subtraction property of equality and combining like terms on the left, we end up with negative 4 equals negative x. So that means that x equals 4. Well, if x equals 4, then we can take this and say that y equals 4 plus 1, so y is equal to 5. So if x equals 4 and y equals 5, then it would make it so that PQRS was a quadrilateral. And it really doesn't matter which of these values you solve for first, x or y. In a system of equations, they will always come out being the same. Let's take a look at another that relates to theorem 6.7. Here we have a set of 3, or more in this case, 4, parallel lines that have a series of transversals interacting with them. Now, as we look at them, I'm going to tell you to begin with that EF, the length of EF is equal to the length of FG, which is equal to GH, and all of them are 6. And AD is equal to 15. What I want to know is what is the length of BC. So what we have to do is take a look here. As we go through, EF, FG, and GH are all 6. So let's label those 6, 6, and 6. So what we have is a transversal. EH is a transversal, and it is being cut into congruent segments. So that means every transversal of these parallel lines are also cut into equal segments. Well, AD overall has a length of 15, and that's what moves across here. And it is split into 3 equal sections. So in order to find the length of any one of those sections, what we're going to do is we're going to take our 15 and divide it by the number of sections, which is 5. So any one of these, AB, BC, or CD, are going to come out to be 5 units in length. So the properties that we have in all these theorems are very easy to relate one to another and to help to establish rules, lengths, and properties of these parallelograms. So make sure that you have this long list of theorems down and ready to use, because we'll be using them as we move forward through our study of quadrilaterals.